We are the Science Cowboys. We shoot science from the hip.
Today, we present the project on the solar energy harvesting with the Orientable light collectors. In 2017, this project won the Jansport prize at Hydro-Québec Science Fair Régional de Montréal. Also, in May 2017, this project was presented to the Minister of Science of Canada, Honorable Madam Kirsty Duncan. We start with introduction and motivation. First, let's review the main sources of energy on our planet. Currently, fossil fuels are used to produce 85% of all the generated energy. However, they will be exhausted in several centuries. Thus, it is a non-renewable energy. Currently, solar energy represents less than 1% of all the used energy. However, our planet receives more of the renewable solar energy than the energy generated from all the fossil fuels combined. Therefore, we have to find efficient ways of solar harvesting. Now, let's review the technologies of solar harvesting. Solar panels offer a direct way of conversion of light into electricity. However, this technology suffers from low efficiency of 10 to 30%. Another way is the conversion of light into heat and then into electricity, which constitutes an alternative method. This technology is very efficient, however, technologically difficult. We also know that solar energy is distributed on the Earth's surface very non-uniformly. For example, in Montreal, Canada, we only get 150 watts per square meter of solar energy. Considering example of heating a teapot, if we cover the whole roof of a house with solar panels, we can generate 2,000 watts of electricity. To heat up a teapot that contains 1 kilogram of water with that amount of power, it will take 3 minutes.
Main ideas behind our experiments. First of all, let's talk about the main problem for efficient solar collection. For stationary solar concentrator, efficiency of the light collection will change depending on the time of the day because of the sun movement across the sky. A solution to this problem is an orientable solar concentrator. By constantly orienting itself toward the sun, the light concentrator ensures efficient light collection at all times. However, an orientable sunlight concentrator is a complex machine. It first has to find the position of the sun in the sky. Then it has to change the position of the light concentrator using the mechanical motors. In order to realize orientable solar concentrators, we use the robotic kit LEGO Mindstorms EV3, which contains a computer, an electric motor, a light sensor, and a software LabVIEW which controls the computer. Hypothesis of the experiment. Using orientable solar concentrators, we can enhance efficiency of the solar energy collection. Methodology of the experiment. First, we start with local search algorithm for the maximum of the sunlight. As the sun travels across the sky from east to west, we can find the direction of the maximum solar emission by turning the robot to the right until the maximum of the light intensity is achieved. To accomplish this task, we made a two-step algorithm. Step 1. First, we measure the intensity of light, then turn. Then we measure the intensity of light again. If intensity of light measured is higher than previous intensity, then accept movement. Step 2. If not, robot returns to previous position. This slide summarizes the local search algorithm. For completeness, we also present the LabVIEW code implementing the local search algorithm. We also developed a bidirectional local search algorithm, which is an improvement on the previous algorithm. With this algorithm, we first turn right and verify if the light intensity increases. If yes, continue turning to the right. Otherwise, change the direction and continue turning to the left. Finally, we conclude that the local search algorithm is simple to implement and uses a small number of moves. However, it can fail to find the absolute maximum of solar light intensity in case of a complex illumination like a clouded sky.
Now, we present the global search algorithm of the maximum of light. In order to find the direction of the absolute maximum of the solar light intensity, we first perform a complete scan of all the angles from 0 to 360 degrees. After the scan, the robot is turned to the angles corresponding to the brightest light detected during the scan. This is a two-step algorithm. Step 1. First, we turn the robot and scan all the possible directions. As a result, we find the direction of the absolute maximum of the intensity of light. Step 2. After the scan is complete, we turn the robot to face the maximum intensity of light. For completeness, here we present the diagram of the global search algorithm. And here is the LabVIEW code implementing the global search algorithm. To summarize, global search algorithm finds reliably the maximum of solar light intensity. However, it is long to run and it consumes a significant amount of energy because of a large number of movements. Experiment realization. 2 prototypes were developed to confirm that orientable light collectors are more efficient than stationary ones. First, we talk about light collectors in the form of a lens, conversion of light into heat. As the sun moves in the sky in vertical and horizontal directions, in order to find the optimal position of the light collectors, that local search algorithm is applied twice, first in the horizontal direction and then in the vertical direction. The aim of the first experiment is to heat the beaker to as high temperature as possible. The sunlight is collected by a lens and then focused on a beaker filled with a table salt. Changes in the salt temperature over time is recorded with a thermometer. Here is the video of the experiment that took the whole day. In the video, we can see that the robot slowly turns to the right by following the sun. We can also see a bright spot of the focused light on the charred beaker. The sun tracking algorithm works well as the focused light spot always stays on the beaker. Only at the end of the day, when the sky became cloudy, the robot fails to track the sun correctly. Here we summarize the results of the first experiment. In blue, the data is for the orientable collector, and in red for the stationary collector. For an orientable light collector, we observe an almost constant temperature of the beaker, 55 degrees Celsius, throughout the day. On the other hand, for a stationary collector, the temperature of the beaker varies greatly during the day, while its maximum is only 48 degrees Celsius.
Second, we talk about solar panel, conversion of light into electricity. The light is first harvested by a solar panel, then it is transformed into electricity, which is finally stored in a rechargeable battery. The amount of electric energy generated is measured by the LEGO energy meter. The purpose of the second experiment is to collect as much of the solar energy as possible using a solar panel. Here is the video of the experiment that took the whole day. The robot uses a local search algorithm to track the sun position. From the video, we see that the robot turns slowly to the right. The sun tracking algorithm works well as seen from the left panel of the video. This was taken by the camera mounted on the robot, and it shows that the solar panel faces the sun most of the time. Here we show the results of the second experiment. In blue, we show the data for the Orientable light collector. In red is the data for the stationary light collector. For the Orientable solar collector, the generated electric power is almost constant and equals to 0.45 watts throughout the day. The total energy generated during the day is 11,020 joules. For the stationary solar collector, the variation of the generated electrical power during the day is more pronounced. The total energy generated is only 9,940 joules.
In conclusion, the hypothesis of the experiment is correct. Using the Orientable solar collectors, one can indeed enhance efficiency of the solar energy collection.